Welcome to my introduction on logarithms, and I'm just going to enter a few numbers into my scientific calculator. Let's say we start with log of 0.005, and we hit enter, and we get negative 2.30103. Now if you just look at those numbers there, the 0.30103 will seem to recur quite a bit here. So let's try the log. Instead of the log of 0.005, what about the log of 0.05? And we just, reduce it by one negative power. And we end up with negative 1.30103. And so that means that the power has gone down to minus 1. If you think about this as a power of 10. The log of 0.5 is negative 0.30103. Now, it means that the log really, what it's doing is it's handing you the exponent as if it was 10 raised to some power. And so every time we go up one power of 5, the logarithm becomes less negative, because that would be the exponent on 10. And as you can see here, the log of 5 is now positive 0.69897, and again, slight bit of mystery there as to why that would be, but if we take the log of 50, you see that this trend continues. A 1 is added to the front of the number. The rest of the decimals are identical. Well, 500, if we take the log of 500, the reason it's 2.6989700 is because really that's 5 times 10 squared, and you're really taking the log of 5 and adding it to the log of 10 squared, which is going to be why your decimal begins with a 2. And of course, taking the log of 5,000 means your decimal begins with a 3 in front of the decimal, and the equivalent of the log of 5 after the decimal. Solving log equations. Well, let's solve for x here, and bring them. We take the anti-log of both sides, and that means we blow away the brackets and the log expression, reducing the left-hand side to 9x plus 7, and the 1 becomes a 10 to the power 1 because it's an anti-log. The log is the reverse process, where the log of 10 is actually 1. 9x equals 10 minus 7 equals 3. So we're just bringing the 7 over, and then finally we divide both sides by 9 and we get 1/3. Here's another one where we're going to solve, except this time we're going to use a base 3 log, and that means that if we add 1 to this log we get 0. Well, we can bring the 1 over to the other side, and then we get a minus 1 to reckon with. And that means that t minus 1 is going to be 3 to the power of negative 1, because the negative 1, of course, is the log, and that's the log, that would be the exponent if it were raised for a base 3. That's 1/3, and then add 1 to both sides, and then you end up with t equals 4/3. So I'm just going to review a few laws of logarithms. For example, I think the most useful law of them all is the power law, and that's where if you have the log of a raised to a power, then the power can actually go in front of the log expression. It's very convenient, gets you out of a lot of mess. Now, taking the log of a times b would make it equal to the log of a plus the log of b. So the log of a product is really the sum of two logs. And finally, the log of a quotient, a over b, is really the difference of two logs. It's the log of a minus the log of b. Here we begin with both sides being expressions with exponents in them, and now I'm going to take the log of both sides, and I'm going to take the base c log of both sides. Now the log base c of the same base, c raised to the x, is just going to be x by the power law. And using the power law on the left hand side, b goes in front of the log, and we still have the b times the log base c of a. Now this is just going to be x log base c of c, but the log base c of c is always 1, so really this reduces to x. So x equals b times the log base c of a. So if we now look at this, we can now replace the x on the c with b log base c of a, and both sides are equivalent. Here we're going to find the solution between two log expressions, and notice there's a subtraction here. That means the quotient law comes into play, that the difference between two logs is really the quotient of what operands go into the log functions. So log of p plus 5 minus log of p plus 1 can be rewritten by the quotient law as the log of quantity p plus 5 divided by quantity p plus 1, all passed into the log function. This is still equal to 3. Now we take the anti-log of both sides, p plus 5 over p plus 1. This is now equal 10 to the 3. Well, 10 cubed is really 1,000. And this is all from taking the anti-log of both sides of the equation. Multiplying both sides by p plus 1 gives us p plus 5 plus 1,000 times p plus 1. And if we blow away the brackets and gather our like terms, we can solve for p. So here p is negative 995 over 999. Now how about if we use a square root of a? Now remember, a square root means a is raised to the power of 1/2, and by the power law we can bring 1/2 in front of the log expression. So let's see how this works for other expressions. The log of the square root x squared minus 3x equals 1/2. Let's solve for x. So notice that by the power law, the 1/2 from the square root goes in front of the log, and x squared minus 3x is still passed into the log. We can now divide both sides by 1/2 and say that log of x squared minus 3x is equal to 1. And now let's take the anti-log of both sides. And that means that x squared minus 3x is equal to 10. Now we can solve a quadratic. X squared minus 3x minus 10 equals 0. And that factors rather nicely. x minus 5 times x minus 2 equals 0. So x is either equal to positive 5 or negative 2. Sorry, that should be x plus 2. Now, it might come to mind that since we have two answers from this quadratic, are one or both of them the true answer? Well, it turns out that if you plug either one of them into the original function, actually both of them work.